Okay. So we have recalling where we left off last time. Found that the V derivative of a vector y in the direction of the flow generated by the vector field x was the same as the V bracket commutator between the vectors x and y. Depending on the context in which you encounter these things, sometimes called V brackets or commutators. In the context of differential geometry, they're usually called the V bracket. In the context of the algebra, this is called commutator. We'll explore some of the consequences of this V derivative a little bit today. So I want to show you two things. One is I want to show you that we can apply the same definition of the Lie derivative to other objects, so functions on the manifold. In the first one, because we define what a function is, and we understand how to evaluate the function at different points, and then subtract them. And the second, I want to start by giving a geometrical interpretation of what this V derivative is and what the we have an interpretation of what the V derivative is. I'll give an interpretation of what this equation means. The fact that the V derivative is equal to this commutator, the V bracket, and that's what this picture is about. I'll elaborate on this now. And then I'm going to show you how we can use the definition of the Lie derivative to compute the Lie derivative of a function instead of just a vector. And then I want to introduce the idea of one forms. We've already talked about them, but maybe not in this context. So one forms that I'm going to introduce are nothing but the covectors that are dual to vectors that live in this vector space. And in particular, the tangent space. So this will generalize for us some of these ideas that we already started off this lecture called talking about is vectors, covectors, tensors, but we talk about that locally on flat space. What we're trying to do now is generalize this idea to a general manifold. I've already shown you how this would work with a vector. We can define what a vector was. We can define a vector field. There's arrows on this manifold, so some smooth assignment of an arrow to a point of the manifold. That was a vector field. So these are these vectors x and y that are vector fields. And I showed that that you could assign a tangent space to a particular point, and these vectors live in the tangent space at that particular point. So that's kind of taken the definition from curved manifold, general manifold, and brought it back down to something that's locally flat. That's the tangent space. Okay, so let's revisit this flow generated by the vector fields y and x. And I'll show you the interpretation of this V bracket. So suppose that sigma of s and x and tau of t and x are closed, generated by x and y respectively. And I want to start at some point x in f. So we'll firstly start at point x. Okay. And then flow to a distance epsilon along sigma, and then delta along tau. So we start at x, we flow to sigma, and then delta along tau. And then we compare with what happens when we get to, if we start at x, flow to delta, flow along delta to tau of delta next, and then along epsilon to along the flow sigma, right? And then I'm going to compare where those 2 points get us. So flow along sigma, and then flow along tau first, and then sigma, then compare the two. So if we start at x, move some distance epsilon along sigma along the red curve, we'll get to some point sigma of epsilon and x, and then flow along tau, some distance delta, we'll get to the point tau of delta and sigma of epsilon x by our method. So starting from x and flowing first along sigma by epsilon, then tau by delta, we'll get to the point tau mu of delta sigma epsilon x. At this point, the first order and small at this point, the first order and small variables delta and epsilon. This is delta x nu plus epsilon x nu x. Which is x mu plus epsilon x mu over x plus delta y nu of x nu plus epsilon x nu of x is nu plus epsilon x nu of x plus delta y nu of x plus epsilon delta x nu of x d mu y mu. Question?
I was wondering what the orders were for tau mu, because it's like the linear approximation of tau, like around that point.
What these were like in some chart.
That's all.
I can pick a set of coordinates for tau, and I'll call those coordinates tau.
Oh,
Okay. Okay. On the other hand, flowing first along R, and then along sigma, those takes us to the point sigma mu of epsilon tau delta x, which is sigma mu of epsilon x mu plus delta y mu x, which following the same logic together gets us to x mu plus delta y mu of x plus epsilon x mu of x plus epsilon delta y mu of x d mu of x mu of x. Okay, so now we can take the difference of these 2 points. So tau mu of delta sigma epsilon x minus sigma mu of epsilon tau delta x cancels out this term with that term, this term, that term, the term linear and epsilon, this term linear and epsilon, and all that's left are the cost terms in epsilon delta. And those cost terms in epsilon delta, you can see, is nothing but the mu component of the Lie bracket between x and 1. So the Lie bracket between these 2 vectors measures precisely the failure to commute, along these 2 flows. So this difference here is measured by the Lie bracket. Okay. Okay. So that's a very nice interpretation of what the Lie bracket is doing to measure the brackets measures the failure good. Okay. So this definition of the Lie bracket that we use, comparing the vector at sigma of x, the vector at x, and then dividing by epsilon, and then taking the limit as epsilon goes to 0 to give us the definition of the Lie derivative, can also be applied to other objects. At this point, the only other object that we know is the function. So let's see what happens if we try to apply the definition to a function. So the lead derivative of function f along the flow generated by x, or this lead derivative of f along x, is the limit as epsilon goes to 0, 1 over epsilon times f evaluated at sigma epsilon x minus f evaluated at x. Again, when this is a small, when epsilon is small, this is f at x mu plus epsilon capital X mu of x minus f of x, and then I can Taylor expand this f. So that's the limit as epsilon goes to 0, 1 over epsilon of f of x plus epsilon x mu d plus things that are order epsilon squared minus fx. Fx capital block with fx. This is order epsilon, so this epsilon cancels with this epsilon. And everything here will be at least order epsilon squared when I do that cancellation. And then I think the limit is epsilon goes to 0, so all of this stuff doesn't matter. Now is x mu dx by dx mu. In other words, x evaluated now. Have we defined it? So the lead derivative of a function along x is just x evaluated on that function. Okay, so now we have the lead derivative of a vector along the vector field, and we have the lead derivative of a scalar along the vector field. Okay. So now I want to revisit a notion that we've already spoken a little bit about, which is dual vectors or covectors. Okay, so we've already talked about this, but you've already learned about it already in second year, when you learned that given a vector space V, you can identify a dual vector space V star whose elements act on V to produce a real number. So the elements of V star take elements of V and map them to a real number through an inner number. Okay. In this case, the vector space in question is the tangent space at the point P, P of M. And the dual vector space is called the cotangent space, and we will denote it by T star here. So associated to the tangent space each n is a view. The vector space and cotangent space E star and then determines map elements of E then real numbers. These elements of the cotangent space are called cotangent vectors. Or in the current context, one forms. And in fact, again, you've already encountered the notion of one forms. Firstly, the simplest such one form is the differential of a function f. Function f see that here. And we can use the duality between cotangent vectors and tangent vectors to between cotangent vectors and tangent vectors define the action of df on a vector. So suppose I have some vector suppose I have some vector v with components v mu in some chart. Then df inner product v, not really an inner product. Typically, when we talk about inner products, we talk about inner products in the same space. The duality between the cotangent space elements and the tangent space element. But I'm defining this thing to be v f, which is right down there, is v df and dx. Okay, so this is how you associate an element of cotangent space to an element of tangent space. And this is the real number that they produce. So this guy here. But we already have expressions for the different. We learned already in the first. So given some given some set of coordinates, let's say x mu, which is the action of the charge on the point P. And this function S. We know that the differential of df and differential of the about first order is what we would normally say df by dx cubed dx nu. Okay. Roughly speaking, by the chain rule. So it's kind of natural to think of these dx mu's as a basis for these one forms. In the same way that in this coordinate basis, in this set of coordinates, d by dx mu was a basis for the set of vectors. Okay. So, and this is a dual basis in the sense that the action of dx mu on d by dx mu, let's say mu, is through our definition there, dx mu by dx mu, which is just delta mu nu. And so this basis is a dual basis to the d by dx mu on the basis of dp on m. Any one form, a general one form on TP star of m can be expressed in the spaces as omega mu dx mu. So again, I start off with my manifold, I pick some point P in the manifold, I use my chart to find a set of coordinates for that point P in our here. In terms of this, in terms of these coordinates, a vector in TP of m can be written as v mu d by dx mu. Okay, obviously we think about this as acting on some jet function, but v mu d by dx mu. Similarly, I can express a general one form in TP star as omega mu dx. Right? Note the position of the index. Okay. The components of one form have downstairs indices, and the components of a vector have upstairs indices, as we discussed in the class. So this means that given such a one form, and given such a vector in TPM, such a vector in TP of M, I can write down an inner product between these two, which is omega v x mu v mu d by dx mu is v mu, sorry, omega mu v mu dx mu dx mu in a product d by dx mu, which is delta mu mu, which is just omega mu b mu. Okay, that's because this inner product we defined is linear involved with arguments. Well, you and and then one final point I want to make today, so I can talk about the usual. Oh, we have defined the one form the same way that we would define the vector as a map between spaces. And as such, it doesn't really depend on us having any particular coordinate choice. Okay, so since our definition of the one form is coordinate independent, I can pick two charts, let's say ui phi I and uj phi j, and then ask about what happens if the pointer, considering all this content, lies in the intersection between ui and uj. So, since our definition of omega is coordinate independent, given two charts, say ui phi and uj phi j, that and a point P at the intersection of ui and uj. I can write omega as omega mu x mu, but I can also write it as omega tilde, so mu dy mu, where x is phi I of p and y is phi j of p. Right, so this point P lies in the intersection between the two charts. In one chart, I pick coordinates x, and the other chart I pick coordinates y. Because this definition was coordinate independent, I can expand omega mu in both those coordinates. Right. But because we also know how the coordinates tell me that this is, in fact, let me do it the other way around. This guy is omega tilde mu y mu, also equal to omega mu x mu. This is phi j p, and this x is phi I. But I also know that I know how the coordinates transform. But that tells me that this guy here, omega mu, is dx mu by dy mu dy mu. Okay. Which tells me that it tells me how the components of the one form said that omega mu tilde is dx mu by dy mu omega. This is the transformation properties of one form, exactly the same way we've learned about the transformation properties of covectors. So I want to stop here for now. On Friday, I will use the idea that we now know what the elements of TP are, what the elements of TP star are, and how to take tensor products to build a general tensor of type let's say Rx. And then I will then extend the definition of the lead derivative to one forms and to checks to general classes. Okay, so then you'll have built up a toolkit on how to differentiate, functions, vectors, platforms, and general classes. The calculus that we're trying to build up is going to involve higher rank objects like this one form. In particular, we're going to work with P-forms in general. P-forms are things that we integrate over P-dimensional surfaces. So I will then define what a I will define a symmetrizing operation and an anti-symmetrizing operation, and use the anti-symmetrizing operation to define for us P-forms, and then we'll talk about what's called exterior calculus. So that's the next pre-lecture.